We are a small company that focuses on high quality automobile applications and libraries. So today I want to talk to you about three things. The first thing is, what do we mean by deeply embedded? Because some people have different ideas and we have a very clear idea what we mean. Then I want to talk about a type-safe low-level driver pattern that we've created that makes it easy to write C++ type-safe drivers. And then finally, I want to talk about our innovative embedded STL. First, I got a little side story. Well, okay, actually, it's a West Side story. So this is the second time I've been to Berlin. The first time was just over 26 years ago, in June of 1989. So those of you who did the math, that would put it before the wall came down. So I was on a high school exchange with 8 others from Oregon, and we got a chance to visit Germany for a month. And we stayed with families in Koblenz on the Rhine River. And then at the end of our trip, we got to spend 3 days in Berlin. So that was an incredible trip. We saw a bunch of sights. But when I agreed to give this talk here, I went through my old photos because I had scanned them in to see if I could find anything interesting about Berlin, because I hadn't been here in a long time. And I found 3 photos. One of them was taken from the hotel room that showed an interesting building. So I spent a few days on Google Maps and satellite photos to try to identify that building, because I had no idea where it was, but I knew that the hotel could see the wall, so that was really cool. And from the other side, I could see this other building. And finally, after I thought about it some more, I realized that the building that I saw was the Staatsbibliothek. And it's a very distinct building. And the other side was the wall. So one day, a friend of mine, we wanted to go out and get pictures of ourselves touching the wall, because we had no idea about this time. So I'm maybe 15. It's really hard to see. It was a tiny little photo that I scanned in. But so we went out there and we took each other's photos touching the wall. And this, little did we know that just a few months later the wall fell. But that trip changed my worldview of traveling, and I've been given a chance to come and live in Germany. I live in Munich now, and so it's been an amazing, amazing adventure. Yeah, so it's good to be back in Berlin again, even though it took 26 years. Okay, so who am I? I've been programming in C++ for about 23 years. I first started writing C++ video games for a company called Dynamics. And that was an amazing adventure. I was an intern at the company. I think I was 19. And so here I was writing video games in C++. But I learned most of my C++ experience by writing reusable libraries at Rogue Wave Software. And at that time, I also was part of the original ISO C++ 98 committee, where I got a chance to write the very, very early version of IO streams. So that has had a huge impact on what I've done. Okay, let's talk about what we mean by deeply embedded. So our systems at ESAR Labs typically have about 500 kilobytes of RAM, maybe about 2 megabytes of ROM. Sometimes in some extreme cases, they're as low as 32 kilobytes. So it's not much memory. It's pretty small. It's big. Okay, good. But our applications, we're squeezing everything we have in there, and sometimes we've got just a few kilobytes of memory left after we've put the application on the device. So in comparison, the average Android app is 40 megabytes. So when we talk about deeply embedded, I'm not referring to this. I'm talking about this. So this is what we have running inside the car. Not much memory. And we're talking slow. At least, okay, relatively speaking slow, 100 megahertz. So another interesting little story, I Googled to find out how much memory those original video games that we were working on in C++, how much memory they required. And I think the minimum was 2 megabytes of RAM and a 486 running at 50 megahertz. So not much different than this, but we had a flight simulator running on it. So that was really cool. Okay, one other thing is that we have to start up our applications really fast. Typically, we have to have them starting up in under 100 milliseconds. We need to be receiving data on the bus, processing messages, doing whatever we need to do within 100 milliseconds. That means we need to start up the underlying hardware. We need to initialize our RAM. We need to call all of our global and static constructors and get everything set up, and we have several hundred of those. Finally, we call main and start our operating system. So we've got to do this all in 100 milliseconds. So when we first started doing this, we did the good C++ technique where we initialized everything in the constructor and good dependency injection, passing things we needed, but we couldn't achieve 100 millisecond startup time. Calling all those constructors took too much time. So we created this idea of a life cycle, which is very similar to like the Unix run levels. So all of our components are organized in run levels. Imagine like with Unix, you've got run level 0 and up to run level 5. And we group these systems into functionality groups. So our CAN transfer, which might be the most important one, because we need to start receiving messages, it's probably running at run level 0, whereas maybe something else is running at run level 4 or 5. So we start initializing run level 0. We call init on all of these things. We get all those set up. Then we tell them to run. Then we tell run level 1 to do init and run. That way we can start up our system and get the most important things running within that 100 milliseconds, because that's really important when you start talking about an automobile. And I'll cover that more later. But also sometimes we need to put our systems to sleep because nothing is happening, so we need to shut things down. So we tell run level 5 to shut down, and then run level 4 to shut down, and run level 3, and then maybe we get woken up. So we then have to go tell our systems to wake back up again. But because we know what run level we're at, we only have to initialize back up the stack again. So it actually is easier to start up our systems and shut them down than it would be if we'd been using constructors and destructors. Actually, that reminds me, we actually don't have destructors in our code. Because if you pull the plug at a car, you turn it off, there's no real need to call a destructor. So we have a few, but mostly we don't, because it takes extra ROM, and it really just didn't add that much value to it. So it's easy just to turn the car off. Okay, so next, I want to get into this type-safe low-level driver API that we've been developing to make writing low-level drivers easy and type-safe. These are the foundation of all embedded applications. There's probably lots of them on this thing, and we need to be able to write them in a safe, easy way. And C++ gives us a lot of tools to do that. And with all API design, it's really easy to write bad APIs, but it's a challenge to write a good API that's easy to use and very hard to misuse. So that's our goal. So we start with, we've got a little driver. It's maybe talking to some little SPI device. We can write 8-bit or 16-bit registers. We can read 8-bit, 16-bit, maybe 32-bit registers from the device. So it's really low level, talking to the underlying hardware at the really low level. So here's an example that we're using. So we create a little device, and we say, okay, I'm gonna call the start device command on this low level piece of hardware. And I pass it some random numbers. I mean, they're not random, they're very specific to this, but if you're reading this code, you have no idea what these things are. If you do a review, you're like, oh, is this a cut and paste bug? Did he just copy it from another piece of code and didn't change the comment? I was like, oh man, how do you know? You've got a specification, but this isn't really isn't that helpful. It's like, get back there, huh? So we start with, this is an example that you'd find in a low-level device manual. You've got some specification that describes your OPM register, tells you that it starts at bit 10, it goes to bit 11. It's a read-write register, that's the access up there, and here's some values you can pass to it. This is really useful information. I'd love to see this in the API, because I can look at the specification, I can see my code, and I can know that I'm doing the right thing. But with that previous example, I got some random numbers. I have no idea. But what can C++ do to help us make this easy? So the first thing we want to do is build up some definition of what these registers look like. So we're going to put ours into a structure, and for each register, we're going to create a little union. So when we look at that document, it told us that these registers use page 16 and address 17. Okay, so that's good. You know, there's one interesting thing about unions. They can't have base classes. You ever wonder why? But it's really going to be useful because obviously these page and addresses, we really want them to be dry. I don't want to duplicate them, but I'm going to have lots of registers in my device. And unfortunately, unions can't have base classes, so we're not going to be so dry as we'd like. Okay, so we've got that OPM register we talked about. And these are the values that we're going to be able to pass to it. Just give us some little type-safe way of doing it. Well, it's not really type-safe, is it? But it's just getting there. Okay, so the reason we made this a union is that I've defined, here's that OPM, and it's 2 bits wide. The control one is 2 bits, and the same thing for the other one. We had declared one of those, and here's the raw value that we're actually going to be interested in sending to the hardware. So one other thing, besides unions not having base classes, but they can have constructors. And so we actually use that to make sure that we don't have uninitialized memory and things like that. Okay, so how would we use this? We defined what we think might be a good description of a register, but does it fit our API of actually being usable? So we'll create one of those control registers, and we want to set these bits. So this is why I had that union in there. I set these bits, and I set the OPM, and I set a nice little value. So that at least is clear if I read the code that I'm setting this register to this value. Okay. So that's a little improvement. That makes it look better. So here's the old code. Those random little bits. I've added a few things to it, but I probably could have did that with some global enumerations or some constants or macros or something, right? So it's okay. I haven't really gained much. But what I did gain was that concept of the structure to describe that register. So when I'm thinking about designing APIs, I like to think about, well, how do I use it? How do I use it safely? If I'm reading this code, this API, can I understand it if I see it for the first time? Can a new person look at my code and understand it? What can they screw up? Can they accidentally reboot the car by doing something simple? So I think about this when I'm designing the APIs for the automobile, and it's important because, I want to make it as safe and easy to use as possible. So really, I've got this device. I create a register to do something. I just want to say, hey, write this. Send this to the hardware. I don't care how you do it. Just send it. So reading, of course, I didn't talk about reading in the first slide because, as you notice, slides are a bit small and you can only really show so much. But we can read in the same way. I want to be able to just create a register, read the values, and start looking at it and processing those values as normal. So we're going to use templates. So what's that old phrase? All problems can be solved by either an extra level of indirection or template metaprogramming. Isn't that how it goes?
It's just first one's outdated.
Okay, so all problems can be solved by template metaprogramming. We'll go with that. So okay, so let's bring in some templates here. So back to my device class. Let's take those read and write 8-bit, 16-bit methods. Let's make them private because I don't really want my developers calling them. They're unsafe and they're dangerous and they're just confusing. So let's make them private. Okay. So let's throw in some templates. Gotta have templates. And for our write method, we'll take some class that has a template parameter. And the read will do the same thing. So in order for templates to really work, we need to define what that register class actually provides? What is in the interface that that template function will actually use? So in order for this to work, we're going to define, back to our union again, what's the interface that the template dispatching will actually need? Not what would be used externally by the developers using the registers, but what's used internally by the implementation. So we got that page and address. We're going to add one more, which is how big is this register? Is it 1 byte? Is it 2 bytes? Is it 4 bytes? Because the previous code, I said I had to write 16 bits, but I don't really want to sprinkle that through my code. Once I've defined it once, that should be enough. And then we need the raw values. We need to know what's the real data that we're sending to the hardware and what size is it. So that's the important pieces that we need in order to actually take a register and send it to the hardware. So we're going to create a struct for each register. You could do it differently if you wanted, but this is the way we've done it to work. So the first thing is template metaprogram. You've got to start with your base case. And this is our register dispatch method. Will be templatized on a size. And this will be, is it 1 byte, 2 bytes, or 4 bytes? So we'll specialize for each one of those. So here's the 1 byte case. Very simple. You just have a write method. I have a read method also. Takes the device, takes the page, the address, and the value, and then just forwards it on the actual underlying device. This will be a friend class of the device because we made those methods private. But the advantage now is that I can just tell this thing to write a register, and it knows how to do it based on the size of the register. So how then does this actually work when we have that write method? So the write method in the device, that template one that we actually want our users to use, it grabs the length value that we put in there, the page and the address and the raw values. That's all it needs. So by defining that API and the register in the union, I can now simply tell the register to write yourself to the device or to read yourself from the device. I don't have to do anything else. I don't have to know that it's 16 bits. I don't have to know that it's 32 bits. I don't have to know anything about it. I define that once, and I can use it anywhere I want. Now, what's also really nice is that the compiler will inline all this stuff. So not only are we worried about how does the API work and how do my developers use it, but I need to worry about performance. Because I've got 100 milliseconds to get everything running, and that's not a lot of time. So luckily, the compiler will take all of that little template magic, and all it does is it generates code to set up the virtual function to actually call the underlying SPI piece of hardware. So anybody notice the bug? Yeah.
You're not using the volatile keyword?
Oh, close, but no.
It's also a bug, though, isn't it?
It could be, yes. That's very true. Bit fields aren't portable. So we were using bit fields. And this worked great until we plugged it into a little endian system. And our whole system broke down. So bit fields, they're implementation defined. The alignment of them is implementation defined. How they're packed into some addressable unit is implementation defined. Basically, they're just implementation defined, and it doesn't work, which is really frustrating.
Once you added writing one value into union, reading from the others is undefined behavior.
See? It's even more of them. But we happen to have a couple of meta template gurus in our team. And so they took the little template meta program and made it even more meta. Because we wanted a portable solution for this. We had this great little description of what a register should look like. And we didn't want to be defeated by unportable bit fields. So we created portable bit fields. So now we've got a bits class that defines what bit does it start at and how many bits it is. And it's got some raw values down there. And it's got an assignment operator that does some bit manipulation that takes the value and shifts it over and assigns it and does all the good stuff that you'd expect from the compiler doing bits for you. And you can has a conversion operator to get the bits out of it. So that's really nice. So let's go back to our specification again, because this is where it really, really starts to shine. So we create our union again, and we create that first one. Now what's really fascinating now is it says, hey, this starts at bit 10, and it's 2 bits wide. Well, that's exactly what our specification says. So now before, we had bit fields that I'm hoping were in the right order. But now we actually can say, hey, bit 10, 2 bits wide. The specification looks exactly like the code. And because we've got some classes in here, we can do some dry stuff. So these values here are the same for both of these registers. It makes no sense to copy them. So our registers can inherit from nested structs inside of our union. And again, bit 8, 2 bits wide. You can actually read this and look at the specification and go, hey, did my programmer make a mistake? Or did he do it the right way? And then the union part at the end gets really nice. I just bring in an instance of each one of these into my union, and it doesn't even matter what order they go in, because these bit classes handle that for you. So I can rearrange these however I feel like it. Then I've got that raw value again at the end that I needed for the template dispatching. So all that magic little, we started with that confusing random numbers calling the device, and now we can just create a register, set these values like we did, and the specification matches the code matches the specification, and it's simple. So that was really nice. And of course, we've got this new template class, so how much overhead does it add? This was the original bit field unportable version that we had, and here we just want to read some values out of it. So reading bit fields from a struct has some assembler instructions, assembly not required though. And then it has, so then for the portable version, the code's identical because we used a nice little conversion operator to do that. So the code is identical. You can't really tell. And interestingly enough, the compiler is smart enough to generate the identical assembler code. The assembler instructions are identical. So our unportable bit fields transformed into a portable version, and the compiler was nice enough to generate the same code for us. So we didn't lose anything. We gained a lot because it's readable now. It follows the specification. So that's really nice. So C++ gave us this great power to create really type-safe, understandable, and readable low-level drivers, which we didn't have before. They look like C code. Templates are required to write the driver, but they're not required to use it. Because, sometimes people can get really freaked out when they see templates. So luckily, you're not required to use them. And there's no overhead with this extra nice portable bit field approach. So that's really nice. Okay. So now I want to get into our embedded STL, unless there's any questions on the type-safe stuff. I can always talk to you afterwards. Okay. So the embedded STL, so the STL, it's a great collection of libraries and algorithms and data structures. It's well tested, plenty of books on it, and you can Google for every question you might have. There's a bazillion Stack Overflow answers on there. Maybe they're right. But we can't use in the automotive industry. This is a problem. Got all this great code that I helped write, but I can't use it. I can't put it on this thing. Frustrating. But why? We can't use dynamic memory. We have no heap. We have no dynamic memory in our code. And frustrating. And exceptions are mostly prohibited. The standard automotive specifications say you can use them, but I've never actually seen anybody using them. So that's a problem. So we've made a decision not to use them. So now we got two things: no dynamic memory and no exceptions. So that's like, well, that's a standard STL right there, right? But the other problem is there's different implementations. We do development on GCC, Clang, Visual Studio, but we deploy on Diab, Wind River, Green Hills. The last thing you want is to be developing and have it work here, deploy it to your hardware and have it crash, because something was different about the STL. And then forget about safety critical applications. And by this I mean, your braking, your acceleration. I don't know if Toyota used the STL or not. I don't think they did. They might have helped them. But why no dynamic memory? This was a puzzler for me when I first joined ESAR Labs, because I had written libraries at Roadway for years, and New and Delete were my friends. We had a really great relationship. I never leaked their memory, ever. Now, maybe once or twice. Don't tell anybody. So I asked one of the programmers there, I said, so why can't I use New and Delete? He said, well, we don't have much memory. 32 kilobytes in the extreme case, or 500 kilobytes in the normal case. And we start allocating stuff, and pretty soon I might say, well, I need 50 bytes, but I don't have it contiguously, so I can't get it. So that's a problem. Or performance. Memory management in New and Delete is not actually that fast. And so we've got 100 millisecond startup time, and we can't have that slope penalty of dynamic memory and freeing things and all the other stuff. But the biggest issue is because we're running on such limited memory, we can't actually look at our code and say, how much memory does this application need at any given point in time? So here's an example. Create a little vector events, right? Pretty simple. Everybody's done this. Let's do a bunch of code. Now let's ask the system, how much memory has been used now? Okay, you put one 4-byte integer on that vector. Okay? Now how much memory was added to the system? How much more did you use at that point? Was the vector full? Did it have to reallocate? Was there already space in it? It's unknown at that point how much was used. If the vector was full and I had to reallocate, what's the reallocation strategy? It's different. Did they create one when they created the vector? Did they override the allocator? Which compiler you're using depends on it. GCC will double. The Plogger version, which is running under the Diab, it grows by the Fibonacci sequence. So you just don't know. And the last thing you want to be doing is, you're zipping down the Autobahn, your brand new shiny BMW i8, and get this message on the screen. Sure, we can start up in 100 milliseconds, but if we're using dynamic memory, that might take 3 or 4 seconds. And I'm telling you, if you're waiting for your car to reboot and you're doing 200 kilometers an hour, that's not a good thing. So we can't use it, right? So we have this limitation. So we created an embedded STL. The embedded STL uses no dynamic memory. It doesn't use exceptions. You can use them, but it doesn't require them. Our containers are defined at compile time. And this was a strange concept for me, because I'm thinking, well, I create a vector. I don't know how big it is. But that's the thing, is we do. We're building the application. We know how many network connections we can maximally support. We know how many messages we might be able to send through our message bus at any given time. We know that. And so we can define these things at compile time. One great thing about defining them at compile time is when I leak my application, I know exactly how much memory my system is going to use. You will not get the out of memory rebooting your car message, because I know when I look at that application, when I've linked it, I know exactly how much memory I've used. Okay, so when we created this, we had a couple of goals. First thing is we wanted to improve the quality of our applications. A lot of the code that we've seen written was using raw C arrays. Because if you don't have the STL, what do? People resort to a raw array. That was natural. Or, if you were lucky, they created their own little containers. But again, these homegrown containers, you've got to train your new developers on them because the API is not the standard STL. So we wanted to eliminate this and create a nice, consistent API. We also wanted our API to look identical to the STL because that's going to reduce training time. You get new developers on board, they can Google a Stack Overflow question for how to use a vector, and it applies to our vector, which is great. We also wanted to use our iterators to make them compatible with the native algorithms because at the end of the day, I don't want to rewrite the entire STL. That's a lot of work. And I've done it once. I don't want to do it again. So we wanted to reuse as much as possible. Now, unfortunately, we did have to remove some methods, and I'll talk about that in a bit, because some of them aren't actually possible to implement. Now, we did have one really serious limitation. It had to work with C++ 98 compilers, because that's what our customers are still using. So that really limits what we can do. Yeah, so frustrating. So much in C++ 11 and 14 we want to use. So when you think about these applications, they define their limits in the code somewhere. So I might have, okay, I got 5 network connections or 5 some connections or something. And so you'll see this a lot. It's just everywhere because they had raw arrays. That's what they had. So how do we make this work with C++ and templates? So the obvious answer is just add a size parameter to the template, right? So you've got a vector, you got a size t, or a t in there, and you add a size. Okay, you're done, right? So this is where the data comes in at compile time. So I'm creating an actual array of data right there. So when you declare this, that's your data. That way there's no dynamic memory, we're not allocating anything. That's the way it works. So then when they take their old C array, it's easy to convert to the vector. Just move values around. Okay, so we've got this. And you know, your junior developer comes along and he starts using it. So well, I've got a vector of int of 10. So I create a function that takes 10 ints. And that works well. You know, next week, another guy says, well, I got 15 ints. So he creates another function. You know, next week, I only got 5, so I'm going to create a 5 one. And, you know, clearly this isn't going to work. But luckily, there's a template guru on the team, right? He said, hey, I'll templatize this function. Hey, easy, right? Yeah, now everything's a template. And there'll be a Hacker News article about the header-only automobile app, because everything's in the header file now. But this is serious code bloat, right? We get many instances of this thing. So that's not going to work. What we really want to do is I want a vector of t. I don't care about the size. Most of the time, it doesn't make sense. So what we're going to do is I'm going to create a little protected constructor here that takes the data point and the size and do the right thing and know that I will use that previous class I created to actually declare how much space I need. So what we did is we created a little declare namespace because that makes sense. It's like I'm declaring that I've got 10 items. So I can declare my containers. But I don't have to use them that way. Because it inherits, the declare one actually inherits from the base class. And it passes the data here up into the protected constructor. So then, when I'm actually using it, I have a vector of t. And, I create my iterators like normal. So the usage of this thing looks identical to the STL usage. The only thing I had to do was declare at some point in my application how much space I needed. And we already were doing that with the raw array. Now I get a type-safe STL container that does exactly the same thing. So I mentioned that there were some forbidden APIs, these things we had to remove. If I got a full container, I can't add more elements to it. I got no more memory. I can't reallocate because it's fixed size. Got no new and delete. What if I resize too big? What if I insert too many elements? These things were forbidden, but they're still in the API. So what do we do? How do we deal with this? Do we fail silently? Do we change the API to return a Boolean for success or failure, and then every program has got to check that? But of course, some functions return iterators, such as the insert, so now I have to return a pair. That makes the API more confusing. So I don't want to do that. Ideally, I'd like to throw an exception, but I can't. And undefined behavior in a car is a really, really bad thing. You just don't want that. So what we've created is a pluggable error handler that fits into the STL. And what this lets you do is you can change the compile time or runtime to say what happens when you do something wrong. So in testing, we use exceptions, because I can. And so then I can actually test, well, what happens if I try to add an element to a full vector? It should call my error handler, so I can actually test that. But in production, maybe I want to reset the CPU, or maybe I want to roll back before I called that. I don't know. But at least the application can decide what they want to do at that point. And what we've done is most undefined behavior will call this error handler, including things like if you call front on an empty vector. I don't want to return a reference to some random bit of memory that's uninitialized. That would be a bad thing. And I want to catch that as soon as possible and not while you're zipping down the Autobahn. That would be bad. Unless you want to see that little blue screen of death in your car. Maybe not. But unfortunately, we can't control everything. You know, if you dereference an end iterator, for example, I can't control that. Or if you call an STL algorithm and reverse the begin and end iterators, I can't check for that. So some of the undefined behavior we can't check for, but the stuff we can, we do. So we also took some of the useful additions from C++ 2003 and 11 and backported them to our C++ 98 version. The easy ones were, you know, the const begin and const end. But we also added the in-place methods, which were really nice because with our embedded classes, our embedded STL, we can insert objects into a vector that doesn't have a default constructor, is uncopyable, things like that. So we've added support for that, which was really nice. But we had to mimic variadic templates with a couple of classes. And we've also added a few C++ 11 algorithms that we thought were sort of useful. Again, no move semantics. We don't have C++, we're still stuck on C++ 98, so that makes it limited to what we can do. So when I first started looking at this, before we wrote this, I wanted to see if there was anything else out there, because I'd rather use something than rewrite it myself. So I did find the Electronic Arts STL, and this is something that they've put out there. It's got a bunch of intrusive containers. They use it in their game development. They've got a few fixed-size containers, but it still uses new and deleted exceptions in the library in some places. So that was, we couldn't use it. And I wasn't sure what their support model was, and we really needed to guarantee that it had really high quality tests, support, things like that. There's also an embedded C++ working group. They're focused on defining how C++ works in embedded environments, but unfortunately they do require modern compilers. And like I said, we're stuck with C++ 98 for several years, where several years might be measured in decades. Just in case you're curious about decades. But I mentioned that even for safety critical applications, we still can't use the embedded STL because there's still too much undefined behavior. And so, you're thinking of your braking or your acceleration or steering applications that are running inside the car, we still can't use our STL. There's still too much undefined behavior. But we are working on creating an ASIL version of this library, that's the automotive standard for safety critical applications. And this will have very little undefined behavior. Dereferencing that end iterator, it's going to call the error handler. Reversing those begin and end iterators, calling an algorithm, that'll call the error handler. Things that were undefined will no longer be undefined. They'll be very well defined. It'll be MISRA certified. and it will have 100% condition decision coverage. So, and it'll be the same version across all compilers. So that's what I've got for today. Is there any questions? Okay.
I have a few, actually.
Uh-oh.
Wouldn't it be more efficient with your vector, rather than deriving from the generic vector, to make it implicitly convertible to it? Because then you wouldn't have that pointer in global memory. You'd have it on the stack, and so you'd have many less of them at the same time, or much less of them.
Well, we typically just have one of those as some global variable.
Yeah, but one for every vector, right?
What do you mean?
Well, if for every size of vector, I have
You have the derived class, that's all.
yeah, but the derived class derives from this base class with the pointer in it, right? And initializes that pointer. So wouldn't that, I mean, if it derives from it and it's a data member, isn't that going on to into global static, whatever that section of
Yes.
RAM is called?
Yes.
Wouldn't it be way more efficient to calculate that at runtime when you want it and then just pass it through as far as memory map?
I have no idea.
Wouldn't also the array view idiom be better in that case rather than faking a vector?
Well, okay, so the way we implemented the vector in the slide is not completely how we implemented it.
Oh, okay.
Because it's not a T of size n.
I was wondering about that.
Because we don't want to automatically default create n of those things. So it's really a byte array that we then use placement new to construct them in place. So it is actually like the vector. The array view is a great idea, and we are looking at adding that for sure. And we have like 8 other containers too.
The other thing I noticed in your slides, there wasn't any volatile. When you're
Do not type this code into your computer.
yeah.
Okay,
But,
just saying.
If you're accessing a register with many bit fields in it, the volatile keyword is going to kill your optimization unless you merge them in some compile time template metaprogrammed manner.
Could be.
And one other thing, there's a lot of hardware registers
Yep.
that have special, like they're clear on read or something. Do you encode that into your template description
So
so
like
that you can catch that statically as well?
Anything is possible.
So you don't yet.
We don't yet. You know, this was something we started working on. You know, one thing about that register API that I didn't talk about was because it's a class, I could make a read-only register. I get rid of the assignment operator, and then you can actually then it shows up with the specification. Like, okay, here's a register. It's read-only. Oh yeah, in the code it's read-only. I can do that because it's a class now, not a bit field. We could do things like you're talking about by creating a special class to
Well, like for example,
Yeah.
with interrupt flags is usually clear on read. So if I read
Sure.
these, they're all gone.
Yep.
With your idiom, how do I read them all? Because if I
Good
want to
question.
just read one bit field, then I'm killing all the other ones.
Good question. Let's talk about it afterwards.
Okay.
Back of the back.
Anyone else? Then? Okay, I'm not gonna mind.
Way in the back.
Michael Wong.
Hey. Sweet, I got a question.
So I wanted to update on some of the issues that you mentioned about. I'm the chair of SG14, the Games Development Low Latency Financial Group. And one of the things we actually deal with is of course, constrained resource environment embedded. So we actually might even join force with the embedded group.
Okay, excellent.
They're not actually an official group yet, which is a shame, and I'm aiming to make it that way. So we have looked at things like EASTL. A lot of the gamers have looked at it. One of the issues you mentioned is exception handling.
Correct.
And we've been going through a brainstorm about how to reduce the cost of exception handling. I can say that removing it outright is completely off the picture. That is just too integral to C++. But
Yes.
I totally get it when you say you just can't use these things because it's so infused into STL. And in fact, if you go to any kind of open source stuff, you can't even use those because they will have exception.
Correct.
But the embedded people have exactly the same problems as the gamers.
Yes.
They cannot, they uniformly turn off exceptions because like you said, you know, to these guys, they look at it the other way. They have to have buttery smooth Hollywood style graphics that cannot be, like, where there's no jitter whatsoever. Otherwise, you just will not buy the game. So there's future in there. I just want to let you guys know if you guys are in the embedded community, Think about looking at SG14 contributor thoughts. We've been putting in, on the issue of compile time knowledge, we've been putting forward a number of proposals as a community, like flat containers, circular buffers, so that the allocation is known right from the beginning. These proposals should be of interest also to the embedded community. So have a look at that.
And so again, that's great, but like I said, we're stuck with C++ 98 for the next 10 or 20 years.
Absolutely, we totally get
While
that.
I would love to use it, I can't.
Right. Right. I'll talk a little more about SG14 in my talk, but
Okay.
I think it's a great way to come to look at this thing.
Anything else? Oh, two in the front here. Take your pick.
You mentioned that embedded STL introduces some sort of undefined behavior and thus cannot be used in absolute critical things like breakers and something else. But by prohibiting this, you encourage people to write things by hand, and this handwritten code is yet prone to undefined behavior. So I wonder, what is additional undefined behavior introduced by STL? I fail to realize any.
The actual issues with, creating an ASIL library, which is what you'd use in a functional safety, a functional Sicherheit library, is more than just undefined behavior. There's a lot of processes to go through to do it in order to use it in steering and braking and acceleration, things like that.
Tool analyzability, like the ABS-in validators, part of that too?
There's a lot with this. So like I said, we're just starting to work on this because I don't want people writing arrays and writing functional, safety critical code, because it's pretty dangerous. You get buffer overflows or you index out of the array. So I want to give these classes to them just to make their job easier and to make that car a little safer. So, two in the front here.
You mentioned a lot of global constructors in your code. Did you ever get into the global constructor call ordering problem?
It's another issue, isn't it? Yes. So if you have all these global constructors, what order do they get called in?
But
So
what was your answer? My answer is forbidden.
well, we can't forbid them, but our constructors don't do anything. They might initialize, the internal data points, but that's where that life cycle came in, is we call init what that does to setup.
But then they're essentially empty, so they're not there.
Correct.
Then you don't have any.
That's why we can start up in 100 milliseconds.
Nice. Using C++ sometimes solicits more conformance requirements from industry. Is it worth the trouble over C?
Oh my God, yes. Oh,
Okay.
undoubtedly yes.
I've heard firms say that it's so much more trouble that just for that reason we stick with C.
It's just, you get so much from C++. Even that simple register thing, you could see it from the code and the specification, they matched up.
I agree with that part, but how much more trouble do you get from conformance requirements and?
Our code is simpler, easier to maintain with C++, guaranteed.
Okay.
Yeah, and if not even a question.
So you only showed the implementation of the vector,
Correct.
which is the most boring of the
I know.
containers. So I would be interested, especially in the node-based container, like a map.
We have those.
What does this look like? I would imagine you probably don't have pointers between the nodes anymore if you allocate them this way.
So we've got vector, array, deck. We got a forward intrusive linked list. We've got set, queue, stack, hash map, a sorted map. The implementations vary depending on what we are trying to solve. I mean, really, our customers are automobile people right now, and so we created, the API is identical, so that's the thing you'll notice. The implementation might be slightly different, but the goal was to, again, get rid of those raw arrays, or at least introduce some data structures to the applications. And so as we go, we keep adding more. And we add different implementations of maps, because sometimes I want a linear-based map, or maybe I want a pair, key and value, depending on the implementation, depending on the use cases. We've got different versions of that. So we keep adding more. But the pattern is still very similar, where you declare your class, how much space you want to have. The map, we define how many, maybe how many keys you might have or how many elements in the map. So unfortunately, I believe I have 10 minutes left. Is that right? Yes, okay, great.
So I actually would have one more question. You mentioned that you do some runtime checks to detect what would be undefined behavior otherwise.
Correct.
Now, I know, like, for example, on Visual Studio, the runtime also does this in debug, and it can get horribly slow if
Totally.
you're unlucky. So, I mean, you're on even slower devices than the typical desktop machine. So, are there any things that you can do there? Like, you only check what is really cheap to check? Or?
Correct.
Okay.
You know, let's say if you have a full vector or an empty vector, you try to call the front method, it's empty, so that's a simple check. You know, if the size is 0, then call the area handler.
But you cannot opt out of the checks. They're
You can.
always on.
You can totally
Okay,
turn them off.
Okay.
And make it completely configurable. You know, when I'm running my test suite, I have them turned on to the maximum so I can check everything. You know, when you run the target, you might turn them off if you know your code's going to work. But it might be better to actually, again, I don't want to impose a policy for people to say, well, you have to do it this way. I want people to be able to choose the way they do it in their application for what makes sense for them. So, two behind you.
Do you have some tools to estimate, given the specification, how much memory resources you will need for your program?
That's a hard question. We typically know, the thing we know is, okay, we know how much memory we have, how much ROM, how much RAM. As we're building the application, of course, that's changing. You add more code that increases your ROM. You add more objects or add more fields or more data to increase your RAM. And so we typically sometimes don't even know how much RAM we need until right near the end. Because we keep, you know, we add things, we fix bugs, how much stack space do we use? You know, if you put more stuff in the stack, that increases things, and it's changing. But we are trying to provide tools to make it easy for us to detect issues that happen. So we know, okay, we will guarantee we fit in space, fit in the amount of memory we have. So it's a balancing act.
So basically, you try to use as little memory as you can always, or
No, I mean,
No.
we want programmers to be able to write code, you know? We don't want them writing assembler. But we want to, so we have to be as efficient as possible in performance and memory. Sometimes you got to make a trade-off. So, you know, we've got 100 milliseconds, so that's the most important thing to start up. And then, you know, memory consumption, like, well, you know, if you think about size T, on a 64-bit machine, that's 8 bytes. But on, you know, these are 32-bit machines, so it's 4 bytes. I'm not sure I'm going to have a vector that's 4 billion elements big. So can I get by with 16 bits, 2 bytes? I don't know. But that's the questions that we start to ask at some point, because we are really resource constrained. So, okay. Next door.
So you can, by pre-declaring sizes, you can get a handle on the global variable sizes, but not the stack. Have you got any tricks for figuring out what your maximum stack size could end up being?
That's actually something I'll be doing for the ASIL version. So for every function in the STL, I will calculate how much stack space that we use, because that's always a question, you know, and of course it's compiler dependent and operating system dependent and hardware dependent and everything else. But if I can give an estimate of, okay, calling the find function in the worst case takes, you know, whatever T is times 10 plus a few other bytes, that will at least help the developers to know how much they might possibly use. So any other questions? Way in the back or in the front?
Again, so there is actually another group doing undefined behavior. So whatever you discover, we really need that information about these we're trying to fix these. Something will never go away, to be quite
yeah.
honest. The second thought, so you have a embedded STL,
Yeah.
and you have these additional containers that you created. I actually am encouraging you to submit some of these to the standard. One of the proposals we've been working on is a dual path for many of the containers, such that so that they're dual error handling path. There's precedence for that because the file system TS and the task TS both have dual handling because they also live in a low constraint environment as well too. So it's not an impossibility. It's not there yet. But for the future, if you don't want to keep rewriting these things, and as you said, you want these things to be addressable exactly as they are on Stack Overflow, the way you do it, then please think about submitting these. We're already looking at intrusive containers,
Nice.
as I said, so a lot of these aren't that far off. So I'd really encourage you or anyone else who have these kinds of containers that are specific to industry. The other way that you can also do it is, I might add, is that the C++ people have just created this thing called GSL. I'm trying to remember what the name means. Guided. What it is, it's almost like a standard lint that allows you to fit things specifically by industry. Okay. I'm pretty sure it stands for Guided Standard Library, and it's essentially like a view of the standard library, which enables you to get us better lint-like messages. But there's also talks about ways of making it fit. For example, better for the automotive industry and things like that.
Yeah,
So, thank
thanks.
you.
Anybody else? No? Okay. Thanks, guys.